Fellow St. John's fifth graders, we're going to look at what may very well be the most important truth, the most important concept of middle school math, and that is of the equivalent fraction or equal fractions. When are two fractions equal? Well, in a previous video when we were talking about what is a fraction, how are they generated on the number line, and which mixed number is a particular improper fraction, which improper fraction is a mixed number. We will work more with that, by the way. You're not expected to understand all of that just from watching that first video. We are going to continue to work on that. But now we're going to look at fractions with different denominators. When we're talking about improper fractions and mixed numbers, the denominators are the same. This, I don't think I pointed that out. It's kind of obvious, but this was the kind of thing we dealt with previously. The fact that 12 fifths, you can think of 12 fifths two ways. You can think of it as the 12th fifth to the right of 0, but it's also the second fifth to the right of 2, right? You can think of 12 fifths as 5 fifths plus 5 fifths plus 2 fifths. Each of these 5 fifths is 1. So we have 1 plus 1 plus 2 fifths, 2 and 2 fifths. 2 plus 2 fifths, or 2 and 2 fifths. These two are equal, they are equivalent, they are the same point on the number line, the 12 fifths and the 2 and 2 fifths. But notice that the denominator of the 12 fifths and the denominator in the 2 and 2 fifths is the same, it's 5. Now we're going to consider fractions that are equal to each other where the denominators are different. And this lesson is also going to depend on dividing a line segment into an equal number of pieces. I've already done that to generate a halves number line. I haven't named or counted the halves yet, but if you look up here between 0 and 1, I've placed a point halfway between. By putting that single point between 0 and 1, I've divided that unit length. The unit length is the length from 0 to 1. I've divided it into two equally sized pieces, 1 and 2. And the same thing between 1 and 2 and 2 and 3. And of course, anything that I do in this limited part of the number line can be thought of as extending forever. There's an infinitely long number line of halves, both to the right and to the left. There are negative halves as well, which we're not going to get into just yet. But we now count those halves. We can think of 0 as 0 halves. And the first half to the right of 0 is 1 half. The second half to the right of 0 is 2 halves. And a very important point is that the whole numbers are halves. You don't skip them. That number 1 is one of the halves, and it is the second half. Then comes 3 halves, and 4 halves, and 5 halves, 6 halves, and we could continue counting these halves forever, just like we count anything. The numerator does the counting. The denominator is how many pieces is the unit length divided into equally sized pieces. So we see here that 2 halves is the same as 1, 4 halves is the same as 2, and 6 halves is the same as 3. We can look at those fractions as divisions. 2 divided by 2 is 1, 4 divided by 2 is 2, and 6 divided by 2 is 3. But now what we want to do is divide each half into 2 equally sized pieces. Now I'm choosing 2 pieces. It doesn't have to be. You don't always have to divide a length into 2 equally sized pieces. You can divide it into 3, 4, 5, any whole number that you want, 2 or bigger, right? If we now take these half line segments and put a point between 2 consecutive halves, dividing that half length into 2 equally sized pieces. Let me do that now. Put a point halfway between 0 and 1 half. Put a point halfway between 1 half and 2 halves. halfway between 2 halves and 3 halves, halfway between 3 halves and 4 halves, and so on. So now I have divided each half into 2 equally sized pieces. Now, think about this for a moment. Pretty easy question. I divided the distance between 0 and 1 originally into 2 pieces to get halves, and then I divided each half into 2 pieces. So how many pieces total are there between 0 and 1, between 1 and 2, between 2 and 3, and so on? There are 4, of course. Let me just indicate them with the marker like this. Starting at 0, but not counting 0, we have 1/4, 2/4, 3/4, 4/4. By the time I get to 1, I'm at 4/4. It's 4 equally sized pieces. Let me indicate them like this. By making a little jump with the pen there. 4 equally sized pieces between 0 and 1, 1 and 2, 2 and 3, forever, and so on. Right? Now we can count the fourths, but just as before, every point up here is going to be one of the fourths, including the halves and including the whole numbers. The first fourth to the right of 0 is 1/4. 0 itself can be thought of as 0/4. The first fourth to the right of 0 is 1/4, then comes 2/4. That 2/4 is, of course, right on top of the 1/2. The next fourth after 2/4 is 3/4, then comes 4/4, and notice, of course, every point that is up there is one of the fourths, including the whole numbers and including the original halves as well. After 4/4 comes 5/4, 6/4, 7/4, 8/4, 9/4, 10/4, 11/4, and 12/4. Let's focus on the whole numbers real quickly. The whole number 1 can be thought of as 2 halves or 4/4. Anytime the numerator and denominator are the same number, the fraction is equal to 1. And you can also think of those fractions as divisions. 2 divided by 2, 4 divided by 4, 1. Then we get to the whole number 2. This is the whole number 2. It's also now known as 4 halves or 8/4. And again, thinking division, 4 divided by 2 is 2, and 8 divided by 4 is 2. And finally, the whole number 3 is 6 halves, but it's also 12/4. 6 divided by 2 is 3, and 12 divided by 4 is 3. But what about the halves that were not whole numbers? Let's focus on those for a moment. The first half to the right of 0, 1/2, is now 2/4. Let me write it this way. 2/4 equals 1/2. And now we look down here to 3 halves, and we see that it is 6/4. So let me write 6/4 equals 3 halves, and 5 halves is the same as 10/4. Let me write 10/4 equals 5 halves. Now, why can I write equal signs between the two fractions? Because they are the same point on the number line. The second fourth is the same as the first half. The 6/4 is the same as the third half. And the 10/4 is the same as the fifth half. They are the same points on the number line, so they're equal. Let's look at this 2/4. Can't we think of it as 1 times 2 over 2 times 2? Right? 1 times 2 over 2 times 2. Well, that's still going to be a half, because 2/4 and 1/2 are the same point on the number line, but we can think of the 2/4 as 1 times 2 over 2 times 2. 1 times 2 is 2, 2 times 2 is 4. Let's look at the 6/4. Let's think of the 6/4 as 3 times 2 over 2 times 2, right? I haven't done anything tricky here. All I've done is realize that 6 is 3 times 2, and 4 is 2 times 2. These raised dots here, the raised dot between the 3 and the 2, these are not decimal points. They're raised up in the middle of where you're writing, so they are multiplication signs. I could have put X's there, but I'll use the raised dot. And 6/4 is still equal to 3/2, even when we write it as 3 times 2 over 2 times 2. The 10/4 we can think of as 5 times 2 over 2 times 2. And 10/4 is 5/2 because they're the same point on the number line. But now we're starting to see how this works in general, according to the symbolism that's up above there. According to this symbolism, we see that A times C over B times C is the same as A over B. And by the way, this double arrow here means that the two statements are equivalent. You can say it either way. You can say that A equals B, but if A equals B, then it's certainly true that B equals A. You can always flip whatever's on the left and right side of an equal sign, you can always flip them around. All right, that's a basic assumption of math, that if A equals B, then B equals A. Doesn't take much explanation. You can't really argue with it. But sometimes it helps to write it in both directions, both ways. So that's what I did up there. But, you know, if you look at these three statements that I've written down below here, this is like A over B, the 1 and the 1/2 is like the A over B, and then what did I do? I multiplied the top and bottom by the same number 2. So these two 2's here are like the C's. And that's true for all of these, right? It's true here and it's true here. I have 3/2, which is like the A over B. Got the A over B here, 3/2. There's the 3 here and the 2, the 3 and the 2, right? The 3 and the 2 here. And I multiply the top and bottom of the 3/2 by the same number C. In this case, the C is 2. Now, why is the C 2 for my particular example? Because I took the halves number line and I divided each half into 2 equally sized pieces. So this is the concept of equivalent fractions. We're going to spend more time with it. I want to introduce a word to you now that's used in math often in different situations. The word is cancel. Now, cancel is kind of a slang, not a very official word in math, but it is one that's helpful if we understand what's meant. If you look back up here at A times C over B times C, you can cross out each of those C's and have an equal fraction, because there's the A over B, right? The statement said A times C over B times C equals A over B. So if you have it written like that, you can just cross those two C's out. You can cancel them top and bottom. They have to be the same number, though. We can cancel each of these 2's and have the 1/2. So imagine you start with the 2/4, rewrite it as 1 times 2 over 2 times 2, and then cancel those two 2's. For the 6/4, rewrite the 6/4 as 3 times 2 over 2 times 2, and cancel those two 2's, and then you have the 3/2, which is equal to the 6/4. Cancel these 2's, and the 10/4 becomes 5/2. This is the simplifying or reducing of a fraction. Now, if you've reduced a fraction or simplified a fraction before, you probably didn't do what I just did. Let's say you've got 10/4, right? What you probably learned to do is you can divide the top and bottom by the same number. You can divide the 10 and the 10 and the 4 by 2, these being the same number, and get 5/2, and then you can be confident that the 10/4 is the same number as the 5/2. I'm not asking you to unlearn that. I'm not telling you that it's wrong. I'm just asking that you see it in a slightly different way. Dividing the 10 and the 4 by 2 is equivalent to rewriting the 10 over 4 as 5 times 2, which is 10, over 2 times 2, which is 4, and then canceling the 2's. Canceling these 2's is equivalent to dividing the top and bottom by 2. But as you go forward, it's going to be helpful to see it this way as the canceling of the 2's. High school students do that with some complex algebraic expressions. It becomes easier in the future if you think of it as the canceling of the C's, right? The canceling of the C's like I wrote up there. All right, so I'm going to pause. Fifth graders, let's get a little crazy, shall we? Let's stop talking about halves and fourths. Those are for babies. We're big kids now. Let's talk about 15ths. Specifically, 10/15. Now, at this point, I'm going to focus just between 0 and 1. And the concept that we're talking about here applies everywhere on the number line, not just between 0 and 1. But to simplify things, let's just talk about this. All right. Before we talk about the real important truth of what a fraction is as points on the number line and dividing distances into equally sized pieces, that's extremely important. But another thing that's important in your development as a math student is to be able to do things abstractly. You know, we'll start by a heavy focus on the number line, but eventually you need to get to the point where you can do this. Let me guide you through it. Give me two numbers you can multiply together to get 10, other than 1 times 10. That's not helpful. Well, 2 times 5, right? So let's rewrite this as 2 times 5. It's still 10, right? And how about 15? Do the same thing there. 3 times 5, right? 15 is 3 times 5. Now, the 10/15, I said we were going to get crazy, but we didn't get that crazy because I chose the 10 and the 15 on purpose because they both have a factor of 5, right? And that's the key here. Because now look at that 2 times 5 and that 3 times 5. There's the general formula up here. I crossed those C's out earlier. Let me put them back. All right, let me uncross them. So you've got A times C over B times C. One of the most important truths in middle school math. You can cancel the C's. And A times C over B times C is equal to A over B. So here the 5's are the C's. And notice this C and this C have to be the same number. So I can cancel the 5's, right? And what's left? 2/3. So according to this truth of math that I've written for you in that symbolism, 10/15 is equal to 2/3. Now, one other word, like I said before, you might know this, what I just did as, oh, I can divide the top and bottom by 5. 10 divided by 5 is 2, and 15 divided by 5 is 3. I get 2/3, and I just simplified that fraction. And it's not wrong, but it's important to be able to see it as this cancellation of the 5 that's being multiplied by the 2 and the 5 that's being multiplied by the 3. You might have noticed earlier that I mentioned reducing a fraction and I used the air quotes, right? Well, it's a bit of an unfortunate word. What we mean when we reduce a fraction, this is an example of reducing a fraction. 10/15, and we say that it's equal to 2/3. And we use the word reduce. Reduce means make smaller, because the 2 is smaller than the 10 and the 3 is smaller than the 15. But the value of the fraction is not being reduced. That's why it's sort of it could be a misleading word. We're not making the 10/15 smaller because it's exactly equal to 2/3. If two numbers are equal, you're not making it smaller. You're making the numerator and denominator smaller, but the overall value of the fraction is not being reduced because you're coming up with something equal to it. So an alternative to reducing is simplifying. That's the word I prefer. I'll use reduce. I learned reduce when I was your age. But I think a better thing to call it is simplifying a fraction. It's simpler to think of 2/3 as opposed to 10/15, and especially if the numbers were very big, to be able to write the same fraction using smaller numerator, smaller denominator might be a great advantage in helping you understand the fraction. So there's a little word about reducing a fraction. Let's always think of air quotes and a little bit of a wink when we talk about reducing a fraction. Okay. Why does this work? All right. I'm going to first make the thirds number line. Now, I know I started with 10/15, but I'm going to start with a thirds number line and do a little quick math up with you as I use this meter stick. This is a meter stick. The length of it is 1 meter, which is a little bit longer than a yard. It's about a little bit more than 3 inches longer than a yard. Most of the world bases their measurement system on this length called the meter, and all the other measurements that come from it are called the metric system. Here in the United States, we sometimes use the metric system, but we're still using a system of measurement that's much older than the metric system. When we're talking inches, feet, miles, that's much older than the metric system. Someday, maybe the United States will use the metric system exclusively, but, you know, I've been hearing that for literally 50 years or so. We've made some progress, like, for example, you might have heard of 5K or 10K road races. Well, the K stands for kilometer, which is 1,000 meters. So we get the metric system there. When you buy soft drinks, sometimes you buy them in a 1-liter bottle or a 2-liter bottle. That's the metric system. And someday I'll explain to you how all of those metric measurements come from this length, the meter. But for now, let me just say that if you divide the meter into 100 equally sized pieces, it's like the number line. You know, think of this as 0 to 1, and you divide it into 100 equally sized pieces. That's actually done here on the meter stick. Each of those is known as a centimeter, C-E-N-T, cent meaning hundredth, right? What I did here was I made the distance from 0 to 1 up here 60 centimeters, which is more than half a meter. It's 6/10 or 60 hundredths of a meter. I use 60 because, and this is something we'll talk a lot about, 60 has a lot of factors. There are a lot of whole numbers, pairs of whole numbers that multiply to 60. So math is a great tool. And if you think about what you're doing, you can sometimes accomplish a goal by thinking about the math. People that we call engineers and architects use math to build things, buildings, bridges, and so on. Math is very useful. So it's 60 centimeters up here from 0 to 1. That means if I want to make a thirds number line, I can go every 20, right? 20, 40, 60. All right, let me do that. There's 60 centimeters right there. All right, I'll put a dot at 20 and a dot at 40. Now I've got a pretty decent looking thirds number line, right? So this is 1/3, 2/3, and the 1 is 3/3, and the 0 is 0/3. So there's a thirds number line. All right, ladies and gentlemen. How many pieces do you think I'm going to divide each third into? You should be able to answer that. I'm trying to demonstrate now for you why is 10/15 equal to 2/3. How many pieces am I going to divide each of those thirds into, equally sized pieces? Well, it's right there in the number that I crossed off, the number that I canceled, 5, right? Because if I've got 3 equally sized pieces up here between 0 and 1, and then I break up each of those thirds into 5 equally sized pieces, 5 times 3 is 15, I'll have 15ths, right? Okay, the lights just went out. I just ran a few meters, not nearly a 5K or a 10K, but maybe a 5 meter, 3 meter, ran around the room, and the lights came on. It was amazing. Such power, power. From 0 to 1/3 on my meter stick was 20 centimeters. I want to make that distance into 5 equally sized pieces, so I'll use 4 centimeters, right? Every 4 centimeters. That will get the job done, won't it? And by the way, from 0 to 1 was 60 centimeters. 4 times 15 is 60. All right, so that's an example of the fact that 60 has a lot of factors. So I'm making a 15th number line here ultimately, and it was 60 centimeters long. So each of the 15ths is going to be 4 centimeters. Okay, there's a little bit of math for you. 4, 8, 12, 16, and then 20. I'm counting by 4 centimeters. 24, 28, 32, 36, 40, 44, 48, 52, 56, and 60. Thanks to the meter stick now, we have a really good 15th number line. Let's confirm that it's a 15th number line. I don't want to jumble it up with a lot of writing, so we'll count them together without writing it. 0, I'll write 0 is 0 15ths. We'll maybe write a few of them along the way. All right. 1 15th, 2 15ths, 3 15ths, 4 15ths, 5 15ths. Maybe we should write that one in there. 5 15ths. The 5th 15th is right on top of the first third. After 5 15ths comes 6 15ths, 7 15ths, 8 15ths, 9 15ths, and this is the result we were looking for. 10 15ths is exactly the same point on the number line as the 2/3. So we're really done. But to finish, 11 15ths, 12 15ths, 13 15ths, 14 15ths, and of course we know that the whole number 1 is 15 15ths. Just like it was 3/3 as well. So this is how it works. This is why 10 15ths is equal to 2/3, because they are the same point on the number line. And going back now, think back to when we just had the thirds up there. We had 2/3. And symbolically on paper, what we could have done is we could have taken the 2/3 and multiplied the top and bottom by 5 to get 10 15ths. Now I started with the 10 15ths and then reduced it, simplified it down to 2/3. But you could just as easily start with the 2/3, multiply the top and bottom by 5, and get to the 10 15ths. And that would be indicated here, right? 2/3 is the same as 2 times 5 over 3 times 5. So this is the all-important concept of equivalent fractions. It wouldn't be a bad idea to try to make this formula part of your long-term memory. It's not absolutely necessary right now, but you might as well give it a try. Let me put a big red box around it. Big red boxes mean it's important. For all numbers, as long as b and c are not 0, we can never have 0 in the denominator, but for all numbers, a times c over b times c is exactly the same number as a over b. And you can write it the other way as well. A over b equals a times c over b times c. You can think of it either way. We are at just almost 30 minutes, which is a half of an hour. Why is 30 minutes half an hour? Well, there are 60 minutes in an hour. So, 30/60ths is 1/2. Right? If you have 30 minutes out of a total of 60 minutes, that simplifies to 1/2. There's another equivalent fraction right there. They're everywhere. A little more than 30 minutes right now. So I'm going to close off, but let me just say this again. For most of us normal people who are not geniuses, I'm not a math genius. It's only that I have had the pleasure of living on this earth longer than you have, getting a little bit more experience. That, what I'm teaching you to do now, I could do when I was in 5th grade, but I didn't understand it the way I do now. My goal is to make you understand things better than I did when I was in 5th grade, and to try to get you to understand things the way I do. If you ever disagree with me, if you have a different way of understanding it, maybe your way is good too, and we talk about it. Math can be a dialogue. That's some of the most enjoyable parts of my job that there is talking to students about math, and sometimes it never occurred to me to look at something this way, but your way could be legitimate, and your classmates can benefit from it as well. But the reason I say that the vast majority of the human race is not, we are not math geniuses are very rare. Most of us, it takes time to learn the math. I want you to try your hardest to make the learning come and the understanding come as nicely as it can, as quickly. It's not, we're not going to ever say there's an absolute deadline, you must learn this by Friday. Well, everybody's a little bit different. But try this. Try to commit this to your long-term memory. Now, hopefully 6 times 9 is 54 is in your long-term memory. There are many things that should be in your long-term math memory by now. Let's say by the middle of 5th grade, this is in your long-term memory, but might as well start now. You can always take a fraction and multiply the top and bottom by the same number, get an equivalent fraction. Multiply the a over b times multiply by c in the numerator, multiply by c in the denominator, we get an equal fraction, equivalent fraction. All right, I've gone on. So